Hello students, so in this tutorial we are going to briefly discuss about basic building blocks of computer vision programming, basically deep neural network and convolution, and how convolution works, and we'll also deep dive into the codes, step by step building blocks of convolution in this tutorial. Okay, so first let's start with what are the use cases of computer visions, right? Normally we see that's image classification, we see object detection, neural style transfer. So classification as mentioned here, right? So you probably will have different set of images and you have to classify, let's say, images of dog versus images of fish. Then the same approach can also transfer to facial recognition system, kind of same approach. Then here we have object detection, where what we do this, we try to build this bounding box across the corresponding pixels where it is required for detecting objects. Then we'll also have this neural style transfer, okay, where you provide one image, you provide one style, and it will create the image based on the style. Okay, so these are some different problems in computer vision. Okay, now moving ahead, for any images, right? So let's say this is an image of cat, right? So how normally, we'll see cat as this, right? But cat image is nothing but your, let's say it has 3 channels, RGB channels, and let's say it's a 64 cross 64 times pixel. Okay, so this is the overall array representation shape of the image, and how your computer will recognize this image is something like this. Okay, so it will have 3 filters, 3 channels basically. So RGB corresponds to your red, green and blue, so you can see this 3 number corresponds to your color image, and this 64 cross 64 is the width and height of the image. Okay, now what is the problem with plain vanilla neural network, and what is the motivation for CNN? So let's say you have same cat image, a little bit higher pixel density. So let's say instead of 64 cross 64 you have 1000 cross 1000. Okay, as height and width. Okay, so to train the similar kind of if you multiply, okay, this 1000 so it comes to approximately 3 million parameters, right? So 3 million parameters, and if you, let's say, for any classification, if you implement a simple of plain vanilla neural network, right? So the total number of trainable parameter, that means your weight and biases, will come to approximately around 3 billion. So this is a huge number, right? Though modern computers nowadays are able to train all of these parameters, right, very efficiently, but still it's a huge number corresponding, considering the problems we are dealing with here. So that's why there is a separate architecture called convolution in mathematics. So if you implement convolutional neural networks, this number of trainable parameters will drastically reduce. Okay, so yeah, before going to convolution, how your, let's say, edge detection works. Okay, so let's understand that using convolution. So how our edge detection works, so let's say here we have a 6 by 6 image or matrix. Okay, and this sign, this multiplication sign, is nothing but a convolution sign, and let's say we have a vertical edge detector, okay, which is nothing but simple positive ones in the first column and negative ones in the final column, and the middle portion is completely blank, 0. Okay, so it's a 3 by 3 filter. So how you will do calculation, you will set this one to this one, so this one will come in this 3, and then you do element wise multiplication, and then you sum it up, and then you place it here. Okay, whatever output you will get. So if you do the calculation, you will find this one will be the output. Now again, how this calculation will makes any sense, in the next slide you will see. So let's say this is a similar same 6 by 6 image, right, and this one is a 3 by 3 vertical edge detection, vertical edge detector filter. Okay, so if this filter we do a convolution operation on top of this image, you will see an image like this. Okay, so a sharp lightning or sharp white background you can see at the middle, which indicates that there must be some vertical edge. Okay, at the very middle. So that's how your edge detection filters works. So similar type, so you can see this one are the bright pixels, this one are the dark pixels. Okay, so if you rotate this one, right, completely, if you rotate this by 90 degree, you will find a horizontal filter. That means all the positive ones in, let's say, your top row, all the negative ones in your bottom rows. Okay, and same convolution method, you will find a horizontal filter basically. So yeah, now next comes one important topic is padding. What is padding? So padding is nothing but, if you see the convolution method, right, so every time you perform one convolution method, it shrinks the input image size. Okay, so here it is 6 by 6, after doing a convolution it becomes 4 by 4, right. So to ignore this one or to prevent this one, right, normally we perform padding. So in padding, if we implement a valid padding, that means there we don't apply any padding, and if we apply same padding, that means we want the input and output image shape to be same. Okay, so with padding, how we are solving, or what are the formulas for getting the pixel size after applying padding or without applying the padding is written here. So let's say n is the number of pixel of your input image, f is the number of filters size, and p is the number of padding you are implementing in your convolution. Then your output image without applying padding will be n minus f plus 1 times n minus f plus 1, right. So let's say for a symmetric image that has same pixel in both the sides, so 6 cross 6, so if you consider this example 6 cross 6, so you have your output image with a 3 by 3 filter as 6 minus 3 plus 1, that means 4 cross 4, right. And for making this 4 cross 4 to 6 cross 6, you have to add 2 in both places, right. So that means here also you have to add 1, here also you have to add 1. So that's why plus 2p of padding 1 you will do, right. So both of this will make sense when you apply padding in convolution. Okay, now as I have already mentioned in my previous slide, right, so there are two type of padding. So first one is valid padding, when there is no padding applied, so you will get a shrink output, and second one is same padding, when you actually apply some kind of padding to remain the output. Okay, remain the shape of the output basically. And the next one is striding. So what happens here is, instead of sliding one window, you slide, let's say, 2 or 3 or whatever mentioned, right. So when the filter is first here, okay, then if you use a stride of 2, then the next time you don't go to this 3, you directly go to from 2 to 7. Okay, so that's stride, and this is the formula for stride. So we'll do perform everything in Python completely from scratch. This exercise I have taken from Coursera, so it's I find the best exercise currently in online for understanding convolution neural network from scratch. Okay, and the last important topic of CNN is pooling. So what happens in pooling? So let's say you are performing a pooling on this 4 by 4 image with a 2 by 2 filter, right. Then what will happen with max pooling? From these 4 boxes, it will take the highest intensity, that means this 9. Okay, it will take the 9 and it will shrink the size of the image further. Okay, from this 4 boxes, it will take 2, and then again it will shrink the size, right? So from 4 by 4 you now have 2 by 2 size. Okay, so that's called pooling. So in pooling you also have a stride and also have a filter size. Okay, that means f equals to 2 and s equals to 2 indicates it's a 2 stride filter with a filter size of 2 cross 2. Okay, so why we require pooling? First one is parameter sharing. Okay, and second one is sparsity of connections. Okay, now let's go to the tutorial. So as you have seen in this tutorial, that's it's application of convolution neural network, and we are applying it step by step implementation. Okay, so the first thing that you have to understand is the notation. So A4 here is the fourth layer's activation, W5 indicates and B5 indicates fifth layer's parameter. Okay, so this two will go hands in hands. Okay, activation of previous layer normally gets multiplied with parameters of the next layer. This is the first thing. Xi is the ith training example. Okay, so if you combine both of these two, then what you will get? You will get a superscript L subscript I indicates that ith entry of the activation in layer L. Okay, so this top one L indicates the layer, that means fourth layer, third layer, second layer, first layer of convolution. Okay, and in that layers I indicates, let's say there is 100 nodes, so it's ith node. Okay, so in that way you have to understand every time you are doing calculation in the next couple of minutes, I guess. Okay, and nh and wnc, which denotes nh means your height of image, nw indicates your width of image, and nc indicates the number of channels. Okay, so that thing you also have to indicate, and also they are coming with the same layering indication. So this L means lth layer, this L minus 1 means L minus 1th layer. Okay, so this is the notation thing that you have to understand. Okay, so we'll be requiring numpy and matplotlib. So numpy for doing all the calculation, and matplotlib for doing all the plotting and all. Okay, so this thing will be required, and h5 we will be requiring for importing some of the required packages, basically some util files. Okay, will be required. So let's just run this one and wait for it to complete, and let's take a quick pause here and come back once this setup is ready. So what are the outlines of this notebook, right? What we are going to implement? We are mentioning step by step implementation of CNN, right? So we will be applying all the low level details that normally while we are working with TensorFlow or PyTorch, or let's say what I don't know, maybe SageMaker or Data IQ, we don't have to mention. Okay, so these are only for understanding CNN completely from scratch. Okay, so we'll be applying this convolution windows, we'll be applying padding, we'll be doing forward propagation, we'll be doing backward propagation calculations. And then in case of pooling, we'll be doing same thing, we'll be creating pooling forward, then we'll be creating masking, then we'll do the distribute values for backward propagation, then we'll also do pooling backward. Okay, so these are the tasks that we'll be performing, and we'll be performing one additional convolution, how it works and how an image got how convolution changes images. Okay, that one thing we'll see, how it maps to the features. Okay, feature map it calls in convolution. Okay, so all one thing before we start, this back propagation, right? This thing is not required because normally in any backend, right, your TensorFlow or PyTorch, this backend calculation or backward propagation is normally taken care by the framework itself, but still it's good to understand and learn, right? So yeah, you can see this is how it looks like in case of a convolutional neural network, right? As we have already seen here, in case of convolution. So how it works, it acts like the convolution filter acts upon the image, and then it changes the volume of the image, right, and it creates some feature maps. So this output, we normally in case of CNN we called it as feature maps. Okay, so first thing we have to learn is zero padding, right? So in our notepad, if you see the last one, right, where it is here, so this one, right? So what is the effect of padding and why we require padding, and this two output image shape is much more important, right? So why we require padding? The first one, it to prevent it from shrinking, right, preventing the output image from shrinking. That's the first case. And the second one is to prevent the border side information. Okay, so in images, this border side images, when you are applying CNN, are prone to get less feature maps. Okay, so to prevent that as well, and to get much more feature maps from the border side, we required this padding kind of technology. So we'll first implement that padding. Okay, so you can see zero padding adds 0 around the borders of an image. Okay, so this is an image, let's say. So this is a 4x4 image. Okay, and we want to apply a 3x3 filter, and in output we want to keep the output image or output images volume as 4x4. Okay, that means same volume will be required, same pixel size will be required. So that's where we add, these zeros around this image. Okay, and it is called zero padding. Okay, this technology or method is called zero padding. So what's the benefit of it? So if you see now, this 4x4 matrix or 4x4 image becomes a 6x6 image, right? So when you apply a 3x3 filter on top of it, you will again gain a 4x4 volume. Okay, so because of that we apply this padding technology. Okay, so these are the benefits you can see that we have already mentioned. So how to apply that? We have a method called in NumPy pad, np.pad, where you will be passing the array, that means the image, that means this image, and this image will probably have shapes, and in shapes you will have the width, the height, number of examples, as well as number of channels. Okay, so this is this will be the shape, okay, of the image, where you will have number of channels, you have number of heights, you will have number of width in pixel, and you will have number of channels. So in this case, what we have to change, you have to pad this number of width and number of height and number of width, right? This number of examples and number of channels we don't have to pad, as simple as that. So it's nothing, it's pretty straightforward. It's an array, right? So an image is nothing but an array. Okay, so if we have to pad, let's say this x that we are getting in this function. So how to pad this one? So we'll write x underscore pad, which will be our new object, the padded object that we are going to return from this function, equals to np.pad. So you always remember np.pad is used for doing padding, and then you will have pass the element, that means your image, and once you pass this, then okay, if the first one is m, that means number of example. Do you need to pad this object basically, or this parameter? No. So you will pass 0 comma 0. Okay, do you need to pad height? Yes. So you pass the padding sequence, which is provided here as pad, as an variable. So pad comma pad, then again same thing, pad comma pad you will pass for your number of width, and for number of channels, do you need to pad? No, you don't need to pad. Okay, so 0 comma 0, and this mode is constant. Why it is constant? As we are passing these pads, right, and we are mostly doing a zero padding, so this mode will be constant, and the value of the constant will be 0 comma 0. Okay, so if it's 1 1 padding, then this value will get changed to 1 comma 1. Okay, So that's it. It's a pretty straightforward and simple function that you need to implement to do padding. Okay, so this is how padding got implemented internally in your CNNs. Okay, so when you apply in your, let's say, TensorFlow projects or TensorFlow modules, right, when you, let's say, apply padding equals to same, then this kind of code in background it took place. Okay, now we'll run this. So this function will get loaded into our workspace, and once that is done, then let's say simply create one images, right? So how to deal with this kind of images? So we are creating some random integer, right? np random dot random int. Okay, random number basically, where 4 is my number of images example. Okay, the batch number. Okay, 3 is the width of the pixel, again 3 is the height, and then 2 is my channel. Okay, pretty straightforward understanding. And then we are calling this zero pad, we are calling the zero pad with padding of 2. Okay, and then we are printing the shape of x, the shape of x pad. Okay, and we are just randomly printing the pixel of x and x pad to verify, okay, what are the positions. Okay, so if we run this, you can see this is our original image. Okay, and once we are doing a 2 by 2 padding, right, here we have passed a pad of padding amount of 2, right? So what we are doing, a 2 by 2 padding we are doing, so 2 additional pixels it will add, right? And it will add values as we are doing zero padding, so it will add zeros, which means it's kind of a blackish in images, right? So this is your converted image will look like, right? It will have 2 additional padding in both the sides. So yeah, that's how you implement padding in low level programming basically. Now next, move on to your single step convolution. So we have understood what's the padding, then we'll implement this convolution. Okay, so you can see in this GIF, right, how a convolution works. So you have a 6 by 6 matrix or image, right, and you are applying a 3 by 3 filter. So this 3 by 3 filter will first come here, then go here, then go here, then come here, then go here, then go here, right? And then it will repeat until it completes all the blocks, right? So as we are keeping in this example, basically we are not doing any padding, so we'll have a shrunken convoluted feature map which it called in CNN. And how to get the shape of this convoluted feature map, it is equals to your image size, image pixel in both the side. Okay, n minus f plus 1. So your n here is 6. Okay, f here is 3, n here is 5. Okay, not 6, n here is 5, f is 3, so it will be a 3 by 3 convolution. Okay, you got till this, right? So we'll be implementing the same. Okay, one convolution single step. So simply see what this function is doing. This convolution in single step, it is taking the previous nodes activation function and current layers weight and bias. Okay, so always remember what we are dealing with here. We are dealing in this function with a single layer of convolution. That means one single step only. Okay, that means it should return a scalar value like 4 or 3 or 4. So we are doing a single step value in this function, right? So previous layers activation is required and this layers weight and bias is required. Okay, so the first thing is what we have to do, we have to multiply the weights with the previous layers activation. So to do that, we'll be using np.multiply for element wise product, right? What we have to do, we have to do element wise product, always remember, and not matrix product in this case. So first thing, np.multiply will give me the product of at, a and w, and once that is done, we need to do a summation. So np.sum will provide me the sum, and as we are also including biases, so we have to add the bias of that channel. Okay, so then z plus float of b for numerical conversion, and whatever is the result will just returning that result. So let's say in first case it will return 4 based on the image, as we are not including bias in this filter, right? So it's only the weights. Okay, so yeah, again you see we are creating a random activation of previous layer, then we are creating random weight and random biases. Okay, these shapes are important. Okay, this shape should match with this shape, right? Okay, so once that is done, we are doing a element wise multiplication, and then we are summing up this whatever matrix it produces, and with that summation we are adding this bias term. Okay, and then we are printing the result. That's as simple as that in this code. So if we run this, whatever we will be getting, okay, we haven't run this one, sorry. Okay, now if you run this, you will get this minus 6.99, and this is the expected output. Okay, so what we have done so far, we have implemented a low level of padding as well as a single step of convolution. Okay, bravo. Now next step is implementation of forward pass. Okay, so how we have to do the forward pass, we'll see that next. Okay, so convolution forward, it gives you the previous output activations of the previous layer. Again it gives you the weights, the biases, and the hyperparameters. Okay, so hyperparameters means it contains if there is any padding involved, it contains if there is any striding involves or stride involves, right? So if you see a proper convolution neural network that we have done here, right? So what are the things required for convolution? The filter, okay, the pixel, right, and the pooling, and in the next step here, if there is any stride happens, a striding requires, right, for calculation. Okay, so always remember, in any deep learning programming or whatever you are doing, right, machine learning blah blah stuff, is nothing but programming, and programming in the sense it's nothing but computation. So you are doing nothing but matrix multiplications. Okay, matrix multiplications and matrix calculation is happening in the backyard. So no matter whether it's SVM you are applying or clustering you are applying, it's only matrix multiplication. Okay, so we have to build this function which is called convolution forward, where we are getting this a previous, that means activation, output activation of the previous layer, where we are getting weights, where we are getting biases, and in hyperparameter we are getting what will be the stride of this layer, and what will be the first one is stride and second one is padding, right? So first just we'll go through the shape that is provided. So in case of previous layers activation, m is the number of examples, nh previous is the pixel of the previous activation, and w is the again pixel width, height, and this is number of layers. Okay, number of channels of the previous activation that we got. In weights, same thing, we have to get the filter size. So f cross f will be your filter, then number of previous channels, and the number of output channel. Okay, how many output it needs to get generated. And again same thing we'll get in biases, only if there is 16 number of channels, so we'll get 16 biases each for one channel, and that's it. All the rest of the dimensions will be 1. Okay, and in your hyperparameter we'll get stride and padding, and we'll be use that accordingly to calculate the upcoming pixels. Okay, in the output layers pixels. Okay, this stride and padding, and what it should return, it should return 1z. So this is the convolution output, the linear output basically. Okay, and it should have a shape of m, nh, nw, and c, like it has here, right, only with modified values of nh, nw, and nc, right? And nc we get it from this w, nc is provided here, right? So it looks pretty complicated, but it is actually not if you look closely, right? So how we will get this m, nh previous, nh, w, and nh nc previous, right? will use the shape property of an array, numpy array, right? So this is a previous dot shape. When you are applying, you are getting m, which is your first number of examples or number of batch elements. Then the next shape will give you the number of height or height pixel. Then you get width pixel. Then you get channel. Okay, pretty simple. So once we retrieve that one, we'll do the same for our weight. So we'll get the filter size by getting shape by using shape property of weights. Okay, similarly, and from hyperparameters, so hyperparameters, as it mentioned, right, it's a dictionary. It contains stride and pad. So if you call the dictionary's keyword with stride, you will get the value for stride. If you call the key pad, you will get the value for pad. Okay, so this 3 line is clear, right? So we get all the parameters required for building z, right, which will be the output. Now next one is the new height. Okay, what will be the new height? What is my formula? So to get the formula, you will go here and you will see it's n plus 2p minus f divided by s plus 1, right? So we have just implemented the same thing. nh previous plus 2p minus f divided by s plus 1, and we have made it int for floor. Okay, if it is let's say 5.3, then it should return 3, right? Sorry, it should return 5, sorry. Okay, same thing we are applying from the width, same method. So this 5 line, now it's clear. It's pretty straightforward course, right? And then to get the value of z, right, we have to initialize the matrix. Okay, or the it's not a matrix, basically multidimensional array with zeros, so np zeros for that, and we are passing the shapes. So m, nh, nw and nc, that will give me my initial figure of z, right? That will be the output, and we'll populate that z with the convolution formula. Okay, now first what we have to do, we have to create a previous pad by padding the a previous, right? That is the first step of doing convolution. Okay, so you apply 0 pad, right? 0 pad, we have seen here the function. We are just calling that function, and this 0 pad takes the argument the activation as well as the padding amount. Okay, so it will create our activation as a padded activation. That means whatever output it give provided from the previous layer, it just done one padding. That's the first step. Now we are looping over to all the examples available, because we have to apply the convolution on all the images. So that's what we are doing in this line. Then what we are just selecting, and then we are performing the operation, right? This all, if you see closely, we are just performing the same operation that we have discussed. Okay, and where you can find this calculation, you can find this calculation here. Okay, you can find this calculation here, how to calculate this basically convolution and how to append. So once we are done with this convolution, right, we need to call to update this z, that means your linear function. To update this one, we need to call this convolution single step that we have just built, right, for one single activation. Here we have just built this convolution single step, right? So once that is done, your linear updation, right, that is the return function from this function, is completely done. And once that is done, you just do a assert to make sure that your shape, because already you know the shape, right? So you just make an assert statement that whatever you have created here in this value of z, or in this variable of z, it matches with all of these dimensions. And once that is done, you just save the information for backpropagation. So you create a variable cache, where in this cache you store all this previous information. Okay, these are the new information that's stored in Z, and these are the previous information that will be required for back propagation, and then you just simply return Z and cache. Okay, this Z will be utilizing in the forward pass, and then this cache will be utilizing in backward pass. Okay, now it's once you have implemented this function, okay, you again do some random testing. So you can see that whatever we have performed is accurate, and our testing is matching with whatever the expected output is. Okay, and finally pooling, that means shrinking. Okay, and reserving of your pixels intensity. Okay, localization basically of your pixel, that forward pooling will be applying here. Same method, how to find the shape of the pooling layer, right? And in case of pooling layer, as we know that there is no learning parameters, right? In pooling method there is no parameter it needs to learn, so for NC there will be no change, right? So this three steps we are performing. If you see, similarly we are retrieving the same thing, same formula, same method, then we are retrieving these three information, and once it is done we are doing similar kind of thing. So in case of max pooling, we are applying NP max, okay, on top of that 4 blocks, and if it is an average pooling, we are applying NP min. Okay, and once that is done, we are again reserving the informations for back pooling, basically pooling backward. And after doing one assertion that okay, my newly created pooled layer, right, the shape of the newly created pooled layer is accurate, we are just returning it back. Okay, so this same calculation you can cross verify with this. Okay, so let's just run this function as well and verify that this function is also accurate. Okay, probably it is accurate, I don't know. You can see it's accurate. Okay, so once that is done, there is another case I think for average pooling, and that's it. This is how your convolution computation happens, right? I mean internally these things you did not have to do the coding at all. You just have to understand the process. Okay, that is how internally your CNN works. So if you implement anything from scratch, and if something went wrong, then you have this strong sense of ownership at how to debug and how to rectify things, right? So again, this is very much optional, this back propagation in convolutional neural network, which is not required because mostly in your TensorFlow and PyTorch, right, it is already provided by the framework itself. But it's a similar kind of mathematics and approach, and the codes are also provided, so you can go through it. Okay, and if you have any problem, you can comment it down that you need a special session on this, so I can again repeat whatever I am just saying here, right? All these functions step by step, right? No issues on that. Now next one last thing that I like to discuss here, right? So effect of convolution, right? So here if you see that from Skype datasets, we are just loading ascent. Okay, and once the ascent data set is loaded, we're just plotting it. Okay, so you can see this is the image that will be working and will show the effect of convolution. Okay, so let's just copy this image here. Okay, and get the dimension, and that means shape. So you will see it will be a gray image of 512 cross 512, right? Okay, it's not a colored image, it's a gray image, right? And let's say this is the experiment filter that we are using, right? Okay, let's what was there, 111. Let's create a filter with the example values, right? So it will be 1 0 minus 1. Yep. So you can see that Gen AI at work. So Gemini was providing me some of the suggestions, right? So let's create this filter, and for a moment let's pause. So this is a horizontal vertical edge detector filter, right, that we have just seen in the lecture slide, in the slides. So right, this 101 101 101, right, this one is a vertical edge detector. So let's just cross verify whether it does the uh, detection or not. Okay, so this is the image. On top of with if we perform this, if we apply this convolution along with this filter, what will be the output? So this is the code just for your convolution method. So let's store this one. Okay, let's run this convolution method. So it's nothing but two for loops in both the sides performing convolution, right? So once this convolution method is done, let's, if you just plot this image, right, that means your feature map, you will see all the vertical edges, right, and this filter detects all the vertical edges very correctly. Okay, so this is how you have to understand. From this image you are getting this feature map, right? So this is how your filter works or your convolution works in real life. Now next is the effect of max pooling, right? So this is the code for max pooling. So if you apply this, you will see the localization of the feature map. Okay, if now if you see, from 512 to it reduced to 256, right? So within this 256 by 256 region, it has localized the feature map very accurately, right? So this image and this image has only difference in shape, right? And I think all the other properties of the pixels, it is able to localized mostly perfectly, right? So this is how your CNN works internally. I hope you have gained a lot of insight if you are new into the CNN, and or if you are rewatching it just for fun purpose or whatever. So I hope you have liked this video. If you like the video, please do share, subscribe, and stay tuned with us for more AI videos. Thank you.